Remember when I say delta, I just mean how this perturbation field changes according to a small coordinate transformation. So the way it changes is this one. Okay. Then I got another question that I want to maybe say is that yes. So you know so when I say v, you say. So the forward velocity of my fluid, you have to think as general 3 vector, okay, which is only approximately equal to the value in on the three-dimensional method of Benson-Walker background. It would be 0. But this is like, I call it fake in the sense that this is just an approximation. The real, actually, for 3 vector is U1, U2, U3. Okay, that's and then these 3 coordinates, we write it in terms of the gradient of a scalar plus some v vector I. Okay. Now another question that I got, but what happens to this one? Why don't we consider this vector here? And again, because once we study vectors and tensors and scalar, they all decouple at linear order. It's very much like suppose that I study this system of differential equation. You will see that if I want to know this to study the dynamics of x and y, I really do not need to consider what's happening in the z direction, because they are completely decoupled. Okay? So if I study what's happening on the plane x and y, on the xy coordinates of this particle, whatever, then this thing here, I can just forget about z. It doesn't mean that z doesn't exist. Z will exist, but in terms of dynamics of x and y, it's completely irrelevant. And the other way around, if I study z, I can just forget x and y. Okay? So that's why now I am forgetting this one, actually, but they are there. It's like the z variable. This is like the z variable. Whereas the v and alpha, phi, and all these one are the x, y variables. Okay, so what I want to say. Yes. So I would like now to do a tiny calculation here. Okay. Right. Okay, so what I want to do now, yes. Okay, is actually study a particular case of fluid, which is actually very useful, which is the dust fluid, just to say something how this co-moving gauge may have some link with the synchronous gauge. Okay. Now, in particular, so now we are making the assumption that we have a dust fluid. Okay. This assumption is quite good because anyhow we know that there is dark matter in the universe. Okay. So we are supposing dark matter is, we can model dark matter by means of a fluid whose equation of state is this one. And remember, I need to give another equation of state, which was t equal to 0. Okay. Now, this is a very particular, sorry, what am I talking about? These are the two equations of state, okay? All right. And remember that P was n rho over dn minus rho at constant S. Now, if you put P equal to 0, you will realize that the solution for this will be, M0n, M0n. Now, why don't I put any S here? Because I know that T will be 1 divided by n d rho over ds at the constant n. Because t is equal to 0, rho is independent of S. Okay? So these two, so if I put this equal to 0, I solve for this one. And this would be in general function of S. And then I could put plus a function of S as well, actually. No, maybe only function of S here, actually. But this one sets it to be constant, actually. Because rho cannot depend on S. Okay? Very well. So the solution is this one. Okay? And once more, all these objects here are completely, how can I say, covariant expression, which means it's not background. Okay? I'm going to say it again because this must be clear. When we say that P equal to 0, it's P equal to 0 full stop. Not on a particular background. It's the definition of P for the perfect fluid for dust is 0. So delta P, 0. And when we say that rho is just proportional to n, this is true on any background. On any background, and even at cosmological perturbation theory. We will have that delta rho is equal to m0 times delta n. Not only a linear level, but at any order, if you want. Okay, having said this, why did I want to do this? Because I have the following thing. Now, remember that in general, we were describing, this is another way to remember introducing the chemical potential mu. Mu was defined such that P is equal to mu n minus rho. Okay? And then you will realize that mu in this case reduces to m0. Okay? Because P equal to 0, mu n is equal to rho. Okay? We get this one. Again, this one is true, exact. So mu is only a constant for dust. Okay. So then let me do the dp. Again, so far, for a moment, forget about this. So let me work in a general way. We already done this calculation. This is mu dn plus n d mu minus d rho. And this is mu dn plus n d mu. And d rho, by the first principle of thermodynamics, is mu dn plus nt ds. So this will be n d mu minus nt ds. Okay. Now, So for dust, then dp will be 0, which is equal to n d mu, and t equal to 0. So d mu equal to 0, which is completely consistent with the fact that mu is purely constant. Okay? Now we have that this thing is 0. In particular, its perturbation, what it will be, the mu will be equal to 0. So this is a constraint which is only true in general for dust. If dp, if this will not be 0, then in general we don't have delta mu equal to 0. Now, okay, so good. So let's use this constraint here to say something about how V for dust behaves. Okay, so let me erase this one. This one I will not need it anymore. So this was just meant to show that delta mu must be equal to 0. Okay, now then what is mu? Remember that there I wrote that mu is this one. Sorry, U alpha is this one. Okay? On the other hand, I have that U alpha is constrained by the thing that there's U alpha, U beta, G alpha beta must equal to -1. Okay? So now if I replace U alpha with that relation there, what will you get? You will get 1 divided by mu, that object there, times 1 divided by mu divided by object there, GAB is equal to -1. So mu, I can multiply by mu square, and we'll get that mu square is equal to minus G alpha beta d alpha L plus theta d alpha S d beta S d beta L plus theta d beta S. Okay? Hopefully, I didn't do mistakes. All right? Notice this is true on any background, okay? Because this is always true. This is a general definition for JB. Here, at the moment, I'm not splitting any background of perturbation. As for the moment, this is always true. So notice that, in some sense, mu is not an independent quantity, if I consider in this way, okay? Once I write this equation, that means that mu is perfectly defined out of these things. Always. Okay? Right. So, now, let me consider now the case, by the way, again, here, ignoring vector modes. Okay? Because otherwise I should put A, di, B. Okay? So I'm ignoring it. Here, in principle, I should add a I d beta b I. Okay? But I ignore as the z dynamics. Okay? I completely ignore. Of course, if I want to know how vector behave, then I have to keep only that term, and I can ignore everything else. Okay, so then now let me do the delta, the variation of this one. If I do delta, I will get 2 mu delta mu. Now then I suppose this is a small quantity, this must be background. And then we have minus G alpha beta, delta G alpha beta. I will have a delta alpha L, sorry, background plus theta, delta alpha S, delta beta L, background plus theta, background, delta beta S background. Minus twice G alpha beta, twice because I had to take derivative, variation of this one, keeping this one unchanged, and then variation of this one, keeping one unchanged. Will give you exactly the same contribution because G alpha beta is symmetric. So we'll get 2G alpha beta, D alpha L background plus theta D alpha S background times d beta delta L plus d beta S delta theta plus theta delta beta delta S. Okay? But now I say, okay, so this is perturbation freedom electron through background. On top of that, I say I have dust. And because I have dust, I have to remember that delta mu equal to 0. Okay? Dust. Okay? Because this was exactly what we found before. Delta mu.
T is temperature here, no?
Was that?
T equal to 0 and T equal to 0. T is temperature.
T was the temperature.
And theta dot equal to T.
Yes.
So here delta to theta would be?
Yeah. Okay, hold on. Right. So now we had to evaluate this one on the background, right? Okay, so S is constant. So this one will go away. This one will only select, remember that L dot is minus mu on the background. So this one will remain, but only the 0 component. Beta will be 0. Here the same thing. This will go away because this is background quantity. And this will be select the 0 component. Okay? So we will get equal to minus, because I had the minus here, I will get L dot square times delta G 0, 0. And then we have to evaluate this object here. Now, this will be 0. Okay. This will be non-zero, but only selecting alpha to be 0. And because this is background, beta can only be 0 on the background. Okay? Because this is a perturbation, this must be background. G0I is 0 on the background. So we will get the minus 2 G0, 0 up L dot, and we will have this. Okay? Now remains these 3 points here. Now delta beta S, because this is background, this will go away. Now remains this one. Okay? Theta. But theta dot is equal to T, which is 0. Okay? So in principle, yeah, the solution will be constant, but I set this constant to be 0. Because this is just will be a renormalization of delta S by a constant. Okay? So then this term will go to 0. For dust, temperature doesn't exist. So it's kind of dust loses its thermodynamics property in terms of temperature. It's purely only matter density. Let me remind, so temperature usually in the macroscopic thing comes from, but dust doesn't do this. Dust completely don't feel each other. Okay? Right. So then what remains here is L dot. delta L dot. Okay? So we will get minus 2G0, 0, 0, L dot times delta L dot. Okay? Okay, so we have perturbation here, perturbation there. And this must be equal to 0. Okay. So maybe let me go here. And let me write the results here. So V is equal to minus 1 divided by mu delta L plus theta delta S. Okay, so this is good. So we found that 0 is equal to minus L dot square, but L dot square, remember that L dot is equal to minus mu on the background. So L dot square will be minus mu square delta G 0, 0 up. And then let's see what we get here. Here we get right. For a moment, I got, okay. So minus 2, probably, minus 2, right? Minus 2 G0, 0, but G0, 0 up is minus 1, right? Because on the background, G0, 0 up is minus 1. Because of our choice of time coordinates, L dot, which is equal to minus mu. And then we have a delta L dot. Now, delta L dot, let's write delta L dot in terms of V. Okay? So delta L dot would be the derivative with respect to time, partial derivative with respect to time, of, let's say, minus mu V minus theta delta S. Okay? But we said that theta was equal to 0. And the mu is constant for dust. All right? Rho is equal to m0n, and mu is d rho over dn at constant s, which is m0, which is a constant. Because it's constant, this is just minus mu v dot. But v dot, again, partial derivative with respect to time. Okay, so we had to write delta dot here, so we put minus mu v dot. All right, so then another thing that I had to add here is delta G mu nu is equal to delta G mu alpha, delta G nu beta, delta G alpha beta. Maybe some of you know this relation, but this relation is just coming from this relation here. So if you take derivative, if you take the variation of this, the variation of this, of course, is 0. Delta G mu alpha times G alpha nu plus G mu alpha delta G alpha nu equal to 0. You bring on the other side, you will get a minus. You invert this matrix here, you will get this. Okay? Because here I have a free index, I can invert with respect to this free index. And I get this one. So, okay, let me stay here. So what does it mean, this? This means that delta G, 0, 0 up, and now I have to put G0 alpha, G0 beta, delta G alpha beta, right? Because these are now mu and nu are equal to 0. Now on the background, alpha and beta are only equal to 0. This will be minus g 0, 0 squared times delta g 0, 0. So this means this is minus 2 alpha. Because delta g 0, 0, it's minus 2 alpha. Okay? So this will be minus 2 alpha, so plus 2 alpha. Okay, sorry, I wrote it here. Okay, so whatever. So we get 2 alpha. So then this equation here becomes minus mu squared times delta g up, we said is 2 alpha. And then we have minus, so plus, so minus 2 mu squared, 2 v dot. Okay? So we get that alpha must equal to E dot. Okay, so there is this interesting thing. Is it clear, this one? The fact that I have dust and the fact that I have mu, which is constant, really constant, and delta mu equal to 0, led to the constraint that alpha is equal to v dot. When I say v dot here, I mean the v of dust. Because if you put the v of a photon gas, it will not be true. Now, you see what happens here. If I choose co-moving dust frame, v of dust will be 0. I can always choose co-moving dust frame. Then alpha will be 0. So it's a kind of safe way to introduce something which is similar to synchronous gauge. Okay? Remember that alpha was taken to be 0 in synchronous gauge. But that's not possible in general. But now we are doing a different kind of game. We assume now that dust exists, and I can. So this equation of motion, this is an equation of motion. You see, this is not a choice of coordinate. This comes from some equations. And the equation said that alpha is equal to v dot for dust. Then I can set it equal to 0. It's not that I can set alpha equal to 0. I set v of the dust equal to 0. And because of the equation of motion, alpha will be automatically equal to 0. But this is not a choice of coordinate transformation that set alpha to be 0. It's the equation of motion that I got that sets alpha equal to 0 automatically if v dust equal to 0. And v dust equal to 0 is something that I can choose. So if in your problem you have dust, then you will see that the equation of motion will automatically lead to alpha equal to 0, which looks like you are working synchronous gauge. Okay. Right. But it would be wrong to set alpha from the beginning equal to 0. So what we get from the equations of motion should come from the equations of motion. Not that from the beginning I set alpha equal to 0. When I study, say, this problem in the matter comoving frame, I can set v equal to 0 from the beginning, because that's just a choice of coordinates. We did this even for the background. No? We chose the coordinates for background from the beginning. We set g00 to be -1. So the choice of coordinates one can do from the beginning. So from the beginning, you can choose a gauge. But any other thing, any other equation will come automatically from your theory. Okay, so in comoving matter gauge, we should not set alpha to be 0 from the beginning. Okay? All right. Okay, so this was another point that I wanted to say. Now we had to move on discussing before starting the maple thing, because I want to give you an example of a working example of maple. Okay, how maple works now with the perturbation. I showed you the background. I will do perturbations. And but still, I had to do some introductory things. I'm not sure whether I can make it the whole thing by today, but for sure by tomorrow we will see the maple code. So now what I want to do. Okay, now. Okay, so just summary of what we had to done today. We saw today the use of gauge invariant fields, and I also introduced, let's say, the fourth good gauge fixing, which is the comoving matter frame. Okay. Good. The example that I will show you in maple will be general relativity with a general fluid, only one single fluid. We will see that we learn a lot out of it. Okay? So general relativity, cosmological constant, plus one perfect fluid, which is really lambda CDM with neglecting. I will not say which fluid I have, so it could be, let's say, either early time radiation domination or dust domination and cosmological constant, actually. Okay? So maybe tomorrow. I don't know if we can make it by today, but anyhow. So, okay, so now, because I want to say a few things about the code, I have to say something about, there we go. So what shall we expect? Let's see. Let's do forecast of what we will see in the maple code. Okay? We will have a general Lagrangian, which is, say, square root of g times maybe mass Planck divided by 2 r. So this is the standard general relativity part. Maybe minus 2 lambda, and lambda is cosmological constant. Minus square root of g rho. Remember that how we introduced the perfect fluid, this one. Maybe minus g alpha d alpha L plus theta d alpha S. And I will neglect. So we will consider tomorrow the scalar perturbation, which is the most complicated one. Okay? I will start with the difficult things. Hopefully, I would like also to discuss maybe tensor modes. I want to do that, at least the tensor modes. But we will start first with the difficult part, the scalar modes. So we will have this kind of Lagrangian tomorrow, okay? All right, so now what do we do? Now, this is true for any background, any, written in a general covariant way, actually. And I will not state anything about rho. I will leave rho to be a general fluid for the moment. Then we will discuss particular cases. Then what do we have to do? Well, when I say R here, I mean these complicated functions of the metric. So here there will be a function of G, and G will be given by this. Okay? And because I want to discuss a scalar mode, I will neglect 1, 2, 3, and 4 objects. Okay? Good. Then, okay, lambda is lambda. It's purely constant. No variations on this one. No variable related to that. Then I will have my rho. And rho, if you remember well, the independent variables are J alpha, probably L, theta, S, and probably that's all. Okay? Because you remember that rho, rho is a function of ns, but n is defined as J alpha, J beta, G alpha beta, divided by square root of G. If you remember, this was our definition of the independent variables. Of course, inside this part, there is also G alpha beta, but I was talking about the extra degrees of freedom. Okay? And they are all scalars, except this one. So this one I had to take variation, blah, 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 blah. But what happens that any quantity, let me call it general quantity by A could have indices, actually, but for now, A is just general quantity, will be background plus epsilon delta A, where epsilon, as I said, it's a small number. I explicitly say that delta A is epsilon order. Okay? This I will do for all the variables that I have, all the independent variables that I have in my action. I chose.
So this cosmological constant, does it play any role?
No.
We can do away with this and see the analysis.
No, what happens is that lambda will not have perturbation. But lambda is coupled with the square root of minus G. So it will have a contribution in the Lagrangian because of the square root of minus G.
But observed value of lambda is also very small. So.
No, but that will be background, because that lambda re-enters in the background equations of motion. So I'm not doing an expansion in cosmological constant. I'm doing an expansion in the perturbation variables. Okay. Now, having said this, you will realize that L becomes a function of epsilon. Simple step, but very important. Okay? Because this will be very complicated object function epsilon here, epsilon, very complicated function here. If I write down the full expression considering perturbations. But the point is L becomes a function of epsilon. Okay? Then I theory expand in epsilon.
Cosmological context, then we can drop this.
No, because lambda multiplies square root of G. Square root of G will have background plus first order perturbation, second order perturbation, blah, 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 blah. Square root of minus G is a function of epsilon. It's not independent of epsilon. Yeah, so G alpha beta is a function of epsilon, which is written explicitly there, and in front of this anything here, okay, I forget. So this will be epsilon, 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 and so forth and so on. Okay. Then this will be L when epsilon equal to 0 plus, say, dl over the epsilon, epsilon equal to 0 times epsilon, plus 1/2 dl over the epsilon square, epsilon equal to 0, epsilon square, plus order of epsilon cubed. Okay? Does it make sense? This is as simple as that, actually. This is function of epsilon, and then expand it in terms of epsilon. Good. Now, what is this? Yeah, which is the one we saw on Saturday, probably. Remember that on Saturday, we explicitly evaluated the Lagrangian on the background, which is this one. Because I set to 0 all the perturbations. This R will be perturbation R. I will have a cosmological constant. This will be rho of the perturbations. S was 0 on the background, so this one was removing. I had L dot here. That's exactly the thing that we discussed on Saturday. This thing. And we found this object already useful to find the equations of motion for the background. Okay? Now, what is this? Linear perturbation. This is linear perturbation. Okay. Now, let's see what that will look like. Okay?
But here L is the implicit function of epsilon, no?
Yes.
Yeah.
Implicit. Yeah, you know, once you give it this expression here, this will be, epsilon is here, no?
Okay.
So once you write this, once you calculated your R will be a very complicated expression, very monster expression in terms of this metric here.
Yeah.
I'm considering that metric, right? So very monster expression here. Then I do this expansion in epsilon, so we simplify a lot. The first order with the 0 epsilon order, and then the first order and the second order, and so forth and so on. I can expand in epsilon, this monster object here. Okay? You realize it will be a monster object. Because now this is function of t, x, y, z. Everything here is function of t, x, y, z. By the way, we will see that we can simplify a lot this thing, probably by today, hopefully by today. Okay. But anyhow, so we will expect this one to be a very complicated object, and then we are expanding here. Now, what this will tell us? What do you think this will tell us? Okay, let me remain here on this blackboard, but I will erase this Lagrangian here, okay? Anyhow, this is a bit...
Whether it is an equilibrium point?
What's that?
Whether it is
Aha, very good, okay. Similar to that. I mean, that's in classical mechanics, we would have that, right? This would be like the kind of force. So we are looking for... Okay, so now, let's see what we will expect. Now, this the fact that I have an epsilon here, I have to expect this thing to be linear in the perturbations. Cannot be quadratic, right? Because this is order epsilon. So I may have something like function 1 of the background times alpha. This is a possibility, right? Because this is background times alpha, and alpha is order epsilon. So this thing is allowed. I cannot have di chi, let's say, function 2 of time di chi. And the reason why I cannot have this one is that this must be a scalar. It cannot have a free index here. However, what can I have is this. Di dj delta, okay, delta ij di dj chi. This is something I can have. Okay? Maybe I may have a plus f3 phi dot plus f4 phi double dot plus f phi phi. Okay, I'm putting there things which are possible things. The thing that must be a scalar in these 3 dimensions, okay? So phi is perfectly fine. Phi dot is also perfectly fine. And so forth and so on. I may have maybe f6 alpha dot, maybe f7 alpha double dot. This one will not have it, but let's for now assume that there is. Okay, so we may have something like this. Okay, these are all fine things. We also have gamma. We may have maybe f of di dj delta I delta j gamma, and so forth and so on. If I have a fluid, I may have f9 v dot plus f10 v. Okay, those are all possibilities that can come.
Can we rule out the higher derivative?
Yeah. No. Hold on. This is what we would expect. Is the theory will tell us what we get. So maybe this theory I can.
So right now we can also add terms with phi triple dot.
Exactly. But the point is it must be always linear in the perturbations. Okay? Now, having said this, you realize that this is a Lagrangian. Right? This is a Lagrangian expanded the epsilon. And the Lagrangian comes with integral in dt in dx. So I can do integration by parts. Because we know that the Lagrangian, I can, up to integration by parts, I get the same equivalent Lagrangian. So I can do integration by parts. Now, when I do integration by parts, because this is only time dependent, when I integrate by parts this operator, this will go to 0. Does it make sense? Because here I have spatial derivatives, and the only thing I have here is background quantity. This cannot be dependent on x and y because this is linear in the perturbation. The perturbation is here. This must be purely time-dependent object. So when I do integration by parts, this one will automatically vanish. Okay? So then this thing will vanish. That's perfectly fine. Perfectly consistent with your background. Now, notice that I have alpha dot. In alpha dot, I can do integration by parts. So this one, I can write it as minus f6 dot alpha. Because f6 will be a function of time, so I cannot remove that term there. And for example, this one will be plus f7 double dot alpha. I have plus because I had to do twice integration by parts. And then I will have, this one will be minus f3 dot phi, and this will be plus f4 double dot phi. Okay? So notice that the structure simplifies a lot, giving me something which is of this form. Times alpha plus times phi plus maybe something else. Okay? What do you think these objects are? Who said that? Good, correct. These are the background equations of motion. Why are they the background equations of motion? Remember that when we write down our action, okay, when we perturb the action, this will be the 4x square root of minus g sigma mu nu delta g mu nu. And then we set this one to be 0, right? But delta g mu nu at linear order, if I stop at linear order, this will be alpha. The g00 component, this will be minus 2 alpha. Whereas this one will be sigma 0, 0. So this should give me the Friedman equation. Okay? And what about this one? Phi is not really the, phi is the same, right? So phi in our definition is diagonal. 1, 2, 3, actually. And they are the same. So that this will lead us, phi, to the trace sigma ii. Because there are only, because we have a delta GII is equal to delta G22 is equal to delta G33, which is 2 phi. So this will give me the second Einstein equation. Something proportional, maybe 3 times more the second Einstein equation. But 3 times 0 is still 0. So we get still the equations of motion for the background, and so forth and so on. So this point, I erased. So remember we had the 0 plus dl over the epsilon equal to 0 times epsilon. Okay, so this object here gives equation of motion. Also, in this one, equation of motion. So, but in a different way. This one does not give me explicitly the equations of motion. This gives me a Lagrangian for the background. Then I had to find the equations of motion on that Lagrangian. What we did Saturday. This is one gives me immediately the equations of motion for the background. So this object here will be the Friedman equation. And of course, if I have matter fields, I will have all the equations of motion for the matter fields. So if I set this coefficient to satisfy the equations of motion, this term will vanish. This is very similar, I like the point of the equilibrium point, when we study, in classical mechanics, springs and stuff. We first had to find what is the minimum of the effective potential. So then that will be my equilibrium point. And then I study perturbation out of that equilibrium point. That equilibrium point is in cosmological perturbation theory is found by going to the first point, to the first order and doing integration by parts, such that we get this form here, and then we will have equations of motion. Okay? The whole thing, just to say, this procedure becomes mechanical. Theory expansion, integration by parts. There is nothing very deep into this. The difficult point is to set the, in my opinion, the physics theory enters when we set these variables here. Okay? So this will be interesting because actually many times I find equations of motion. Well, this gives you two choices to find equations of motion, by this way and this way. If you're not sure about one method, if your equations of motion for the background are correct, you can do this to double check. They are consistent. If they are not consistent, there is a mistake in the code, or some assumptions are not correct. So now, in this cosmological perturbation theory, we usually do many double check. Many. So the background, of course, is one of the fundamental things, because if we screw up the equations of motion in the background, the whole thing goes wrong. Okay? So many times we try to see whether we have a means of double checking what we are doing by using different methods. It's a bit long thing to do, but once you do, you are safe. This one will give you sigma 0, 0. Sigma 0, 0. Because alpha would be delta G 0, 0. So what I mean here, this action here, you can write as, because there is a sum over mu and nu, all right? It will be 0, 0 times delta G 0, 0 plus sigma 1, 1 delta G 1, 1, no? Plus sigma 1, 2, sorry. But also 1, 2. Okay, but let me focus now on the diagonal part. And so forth and so on, right? This is what's written here. Now, this is minus 2 alpha. So this will become minus 2 alpha, sigma 0, 0. And what are these? This delta G11, delta G22, and delta G22, delta G33 are all equal to 2 phi. Right? I mean, I have also terms in this object here, but this one was removed because this one I can integrate by parts. So what is left over is this one, this one, this one are equal to 2 phi. So we'll have 2 phi times sigma 1, 1 plus sigma 2, 2 plus sigma 3, 3. That's why I said this one is the trace, the three trace. And this one, of course, each of these is the second Einstein equation. They are all equal, right? For the Friedman equation of motion, the second Einstein equation are all equal for the background. These are background quantities. So this becomes 3, so 6 times the second Einstein equation. Okay, so that's how this thing works. If this one doesn't give you the equations of motion, well, that's very good because you found a mistake in your code. Okay? To find a mistake in the code, it's not such a bad thing because once you fix it, then maybe that's the last mistake you have. Okay? Well, I'm really telling you that this is. When we do these calculations, one has to check, double check. And of course, using this computer software helps a lot because essentially you tell the computer software to do a Taylor expansion and integration by parts, which is all mechanical thing. We could do by hand. Point is that we are slow and we may do mistakes. Yes, sorry. Of course, if I have a scalar field, here I will have delta phi plus maybe F11, whatever, delta phi. If I have a delta I, delta j of delta ij plus F12 of delta phi, this will go away for the same reason, right? Because this is partial space derivative and this is time component only. So when I do integration by parts, dx of a function of t is 0. Okay, so then by doing this, you also have the equations of motion for the scalar field if you have. Okay, so this method, the first order, will give you all the background equations of motion. So it's good, very nice, double check, but it's not enough. We want to study linear perturbation theory. So what we have to study is this object here. That object there. That object there for us will be the key object. So where did I put this? There. Okay. Okay, I may stay here. So then, okay, so now, very well. Now we know that we had to look at this thing here. Let's see why, and let's see what we would expect to have. Well, we may have alpha squared f of 1 of t. F of 1 of t is not that f of 1 of t, okay? Will be another function. Okay, just to avoid confusion, h1 of t. But function in the background only, because alpha squared, so it's already second order. So f1 cannot have any txyz dependence, because otherwise there will be third cubic order in the perturbation. Okay? So this one txy, this is epsilon order epsilon squared. Whatever is left here must be purely time dependent. I may have h2 alpha alpha dot. Plus h3. And now you see the thing becomes complicated because you may have many, many more terms. Because you have many fields and you have many possibilities. You may have also this one. That's perfectly fine. di, perfect. Gives a scalar alpha alpha quadratic. But the big difference is that this one I cannot remove it anymore. You know, if I do integration by parts, this will become minus h4 alpha di alpha. So this is just the standard Laplacian. So it doesn't go to 0. So this one, no matter what integration by parts you do, it will remain. Okay? Right. So we may have this one plus h5, say di chi plus h6 di chi di alpha. These are all possibilities there, which we cannot forget about it. They are all quadratic. Now derivatives can remain, and so forth and so on. Let me give you another example. Plus, let's see. Yes. Let me give you this example. h7 phi double dot phi dot plus h8 phi double dot phi. All these ones are also possibilities. Now, I write them, a few of them, okay? You may expect to have many possibilities, because I have also many fields. You know, here I only discuss alpha, chi, and phi, but now we may have also this kind of thing, plus h9. But in principle, you may have a nabla I chi, nabla I gamma. Or maybe nabla, yeah, you may have. I don't know if you will have, but anyhow, so you may have. Then plus 10, let's say, you may have even the nabla square gamma, nabla square gamma. Okay, when I say nabla square there, nabla square means d over dx square plus d over dy square plus d over dz square. Okay? So Laplacian in Cartesian coordinates. Okay. So we may have all these things. Okay? Now, this little picture here, I consider to be useful for a few reasons, and then maybe we finish. But okay, so let me keep going. I want to do at least I want to finish this part here, which I think is important. Now, suppose that I have a three-vector field. Now, Xi looks very much coordinate transformation. I don't know how to call it. Zeta I. Let me call it zeta I. So zeta I would come from, let's say, zeta mu. Zeta mu will be zeta 0, zeta I. Okay? So before doing the splitting between di and the transverse component. Okay? Okay, so then in my L at second order, we may have this kind of thing. Let me say H11, Xi, zeta I, zeta I. This is a possibility. Okay? Agree? This is a possibility. It's quadratic. We have. Now, let me split now zeta I in di zeta plus xi vector. This one I can always do because this is a general three-vector. So let me split and let me write it here. So I will get H11, which multiplies di zeta, plus I will have 2H11. Probably I will get di zeta, zeta vector I. Plus H11, z vector I, zeta vector I. Okay? I will have this kind of form. I cannot have any other form except this. And the reason here, because it's a quadratic Lagrangian, the only thing that I may have is this. Okay? Then let's see, what do I do here? Here, I take integration by parts. I can do, this is a Lagrangian. So when I do integration by parts, this is special variable. H1 is a function of time. I don't care. And this will becomes minus 2 di zeta vector I. But this is what? 0. Oops. Scalar and vector don't talk with each other. They don't see each other. Because now the Lagrangian of vector modes will be completely decoupled from the Lagrangian of the scalar modes. Because any possible interaction must be of this form. And this goes away up to integration by parts. Whoa! This is an immense, huge simplification. I don't know who developed this. Maybe Lifshitz or other people afterwards. But this is really genius stuff for doing things. Okay. So you notice that any three vector I have, I split completely at quadratic order. At quadratic order. Into vector parts, completely separated to vector parts. It's like I have two Lagrangians. One for the scalar. So the total Lagrangian will be Lagrangian for the scalar, Lagrangian for the vector, and which are completely decoupled. It's like I have xy. This Lagrangian here will be xy plus x dot square plus y dot square. And here I have z dot square minus z square. So the dynamics of this will be coupled, but this one completely decouples. Because there is no term xz. there is no term yz. That's exactly what we find here. Any term which would be mixed goes away because of the transfer condition. If we don't impose the transfer condition, I have all the mode mixed, which is fine, but it's huge, immense, more complicated object to deal with. Okay. Now, however, for a moment, let's think of going at cubic order in epsilon. Okay. Now, if I have a cubic order in epsilon, I could have this one, zeta vector I, zeta vector I. This is cubic in the perturbation. I will have a function here, f h g l what y of t. I will have a background plus cubic order. And this one doesn't go away because this is scalar, scalar. So a cubic order, vector modes, and scalar modes will couple in general.
And this will get second order equation of
Yeah. Exactly. So this goes beyond linear theory. Okay. If I go beyond linear perturbation theory, then I will have a coupling between vector and scalar and tensor mode and so forth and so on. Now, for example, another thing that so, for example, let me study this thing here, di dj alpha h ij. This is a possible combination because this is the tensor mode, which is linear. This is linear, and the derivatives are make a scalar actually. Okay, out of this one. But again, I can integrate by parts. Okay, I will have maybe function of time, maybe h whatever, h12 times this one. Integrating by parts, di will go here. But this is, again, hi is transverse. So this will go away. So once more, scalar cannot mix with tensors in a quadratic Lagrangian. And what about this? What's the problem?
it will remain.
This will remain. But this is cubic in the perturbation. So it's beyond linear perturbation theory. So if I want to do coupling with the vector, I had to do, say, di of this thing. Di zeta j will not be 0, right? Because I and j are different. But when I do integration by parts, this will go away. Okay? So no matter how you do, you work with this method here. This is the genius part of whoever introduced this decomposition. They manage so that the scalars, vector, and tensor decouple at quadratic order. So in the quadratic Lagrangian, you will not see mixed terms. If you see some code, some problem in your code. Okay. All right. So, okay. So this I think we can stop here. But maybe I wanted to say one last thing or not. Yeah, I want to say a few things more. But do I have time or not? I think it's over. Over? Okay, so let's do it tomorrow. Let's do it tomorrow. So tomorrow what I will do is the following. I will discuss the... So tomorrow we see the code, okay? So tomorrow we see the code for the perturbation, and we will probably... The code is a bit complicated, is a bit long, so we will stay a long time. But before having a look at the code, I have to explain how to deal with different terms like this. Because we will have a bunch of terms like this, and we had to find a way how to implement integration by parts in a kind of smart way. May not be the smartest, but try to simplify as much as possible what we have. Okay? Because we saw that here, by integration by parts, it was really crucial mean that we used, actually. Because we have a Lagrangian. Okay, so see you tomorrow, right? See you tomorrow.